Welcome to your video on optimization. So what is optimization? Optimization is taking a resource or a situation and making it most effective. Examples of this would be maximizing profit or maximizing volume, area, perimeter, things of that nature. So before we get into the steps for solving these problems, let's take a look at the first one and see what it looks like. So number one, we have an open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch piece of cardboard and bending up the side. So let's just draw this. All right, here's my cardboard. I have a 20 by 25. I have congruent squares in the corner that I'm going to be folding up, all with length x. Okay. So if I was to draw this with the corners bent up, it would look something like this. Here's the top of the box, my x, my height. Okay, so here, this length corresponds to this part here, which is the base of the cardboard after we fold those up, and that would be 20 minus 2x. And then this side would correspond to this part here, and that would be 25 minus 2x. Okay, so now we need to express the volume as a function of x, because the goal here is to optimize our x, because it's asking us how large these squares need to be to make this box hold as much as possible. So what's the max volume? So really what we're doing is we're finding the absolute extrema. Okay. So first let's express the volume as a function of x. So we have x times 20 minus 2x times 25 minus 2x. Okay, so there is our equation. And the value that we're optimizing is our x value. All right, so now it's asking us to find the domain. So we need to think about that. So it's a polynomial. We know it's all reals, but it has to make sense within the context of this problem. X cannot be less than 0. So we know that for sure. So then as for, well, what's the maximum amount of x? Well, this side here is shorter. If I look at this, I know that x cannot be greater than 10. So 10 is the absolute max value of x. Okay. So let's see. Let's take this, let's distribute this through, which gets me 500x minus 90x squared plus 4x cubed. Okay, so now it says take the derivative, set it equal to 0 or where it does not exist. So we're finding those critical points. So I get v prime equals 12x squared minus 180x plus 500. I set this equal to 0 or where it does not exist, which is everywhere. Let's simplify this. Let's pull out a 4, which will give us 3x squared minus 45x plus 125 equals 0. So I'm going to solve for x, and I get x equals 3.681, and I get x equals 11.31. Can't use this one, it's not in my domain. So this is saying that x, the length of x, needs to be 3.681 to give us the maximum volume. So how do I know what that maximum volume is going to be? Well, I take that x, that optimized value, and plug it in to my original, which gives me 820.528 cubic inches. That is my maximum volume. Okay, on to the next one. All right, here we have a farmer has 800 feet of fencing to enclose a rectangular pen. All right, so I'm already thinking perimeter. Then it says one side of the pen is to be constructed against an existing fence, so no new fence will be needed. Okay. All right. Well, let's just draw that first. So here's my rectangular pen. I don't need a fence on this side because a fence already exists. So let's call this X and this Y. So what are the dimensions of the pen? That can be constructed with the greatest possible area. Okay, so we're maximizing the area. Well, first, I know that I need to express area as a function of x. Okay, so let's see. So what can I do here? I know my perimeter is going to be 2x plus y equals 800. And I can rewrite this as y equals 800 minus 2x. Okay, so before we go any further, let's think about the domain. All right, so x cannot be less than 0, but it cannot be more. If y is 800 minus 2x, it cannot be more than 400. So that's my domain. All right, so let's express area as a function of x. I will take my y and plug it in over here, which gives me x equals 800 minus 2x, which is 800x minus 2x squared. I take my derivative, which is 800 minus 4x, set it equal to 0, where it does not exist. And I get a value of x equals 200. So to maximize the area, my x has to be 200. So the question's asking for the dimensions of the pen. All right, so to get my y value, I plug that back into my original, and I get dimensions of 200 feet by 400 feet gives me the maximum area. Okay, on to the next one. All right, number 3, we have a rectangle has a base on the x-axis, okay, and its upper 2 vertices on the parabola. Okay, here's my coordinate plane. Let's see, the parabola is y equals 12 minus x squared. So my parabola will look something like this. And I know the base of the rectangle is here. And the vertices are touching this parabola. So the vertices will go here. Okay. All right, let's label this. This is y equals 12 minus x squared. We'll call this x. Call that x as well. Okay. So I want the largest area. I am maximizing the area. So I know that area will be 2x, my base, times my height, which is 12 minus x squared. Okay. Let's stop there and think about our domain. I know x cannot be less than 0, and my y is y equals 12 minus x squared. I solve for x, and I know that my x cannot be greater than the square root of 12. All right, that's my domain. Okay, so let's distribute this through, and I get 24x minus 2x cubed. I take my derivative, which gives me 24 minus 6x squared, set it equal to 0. I get x equals plus or minus 2. Can only use the positive value, so x equals 2. So in order to maximize the area, the x has to be 2. Okay, and the question is asking us what is the largest area the rectangular can have. Okay, so I know that area equals 12 minus 4, which gives us 32. And what are the dimensions? They are 4 by 8. Dimensions are 4 by 8. Okay. So number 4, we have 216 square meters rectangular pea patch is to be enclosed by a fence, divided into 2 equal parts. Okay, so we have a rectangular pea patch closed by a fence. Okay, I'm thinking perimeter, and divided into 2 equal parts. Okay. Another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? So we're thinking the absolute minimum value here. Okay, so let's first label this. I know that the area here is 216 meters squared, and this is x, 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 this is my y and my y. So my perimeter for the fencing, because I need it for the middle part as well, will be 3x plus 2y. Okay, so my y, how do I get my y value? Well, I know that the area is 216. So that's x times y. So my y is going to be 216 over x. So I'll take this and I'll plug it in because I need to represent the perimeter function as a function of f. I'm sorry, as a function of x. So I will have 3x plus 2 times 216 over x. All right, so let's think about our domain. Well, x cannot be less than 0, but x can be any value to make this work. So our domain is going to be to infinity. Okay. So let's distribute this through. I get 3x plus 432 over x. Now I take my derivative. My p prime is going to be 3 minus 432 over x squared, and set that equal to 0, and solve for x. So I get x squared equals 432 over 3, which is 144. I can only use my positive value, which is at x equals 12. Okay, so now it's asking me what are the dimensions of the outer rectangle. If x equals 12, I know xy equals 216, so I get 12y equals 216, so my y equals 18. So my dimensions would be 12 by 18. And then it asks what the total fence would be, which we would then plug back into our original. Get 3 times 12 plus 2 times 18, which will give us 72 meters for our total amount of fence that will be needed. So we'll save number 5 for class tomorrow. Have a great day and or night, and enjoy your evening. See you in class tomorrow.